The universe has a baby picture, and it holds its deepest secrets. This is the cosmic microwave background, a snapshot of the cosmos from its first moments. By the end of this, you will know how to read the blueprint for reality itself, from the force of gravity to the nature of dark energy. We are going to decode the subtle ripples frozen in this ancient light. How did a random quantum jitter grow into a galaxy? And what invisible force is pulling the cosmos apart? The answers are written in this cosmic afterglow, waiting for us to translate them. What does it mean to see the universe's very first message? 13.8 billion years ago, the universe was not a void but a blazing fog. This was a seething ocean of raw energy and elementary particles, a plasma so dense and hot that light was trapped, bouncing endlessly from one particle to another. For nearly 400,000 years, this was the state of everything. Then, in a pivotal moment, the cosmos cooled just enough for a fundamental shift. Electrons slowed and combined with protons, forming the very first neutral atoms. In that instant, the cosmic fog lifted. The universe became transparent, and light, for the first time, was set free. That first flash of light has been traveling ever since, a messenger on an unimaginable journey. The expansion of space itself has stretched that primordial light, pulling its waves from the energetic glow of infancy into the long, quiet waves of the microwave spectrum. We now detect this as a faint, cold signal from every direction in the sky, a nearly uniform bath of radiation just 3 degrees above absolute zero. This is the cosmic microwave background. Its discovery was almost an accident. In 1965, 2 radio astronomers named Arno Penzias and Robert Wilson were troubleshooting a persistent, annoying hiss in their giant horn antenna. They scrubbed away pigeon droppings, they checked every connection, but the noise remained. This cosmic static, this whisper from the dawn of time, turned out to be the echo of creation. Its existence was the definitive proof that the universe had a hot, dense beginning, confirming the Big Bang theory. One Nobel laureate, George Smoot, would later describe mapping this background as seeing the face of God, a testament to its profound, almost sacred significance. Yet this cosmic afterglow is not perfectly smooth. Its near uniformity is broken by the faintest of imperfections, tiny ripples in temperature that appear as mottled patches on the sky. These minute wrinkles are the universe's genetic code, the seeds from which everything we know would eventually grow. To read that code, we needed a map. The quest to understand these subtle imperfections leads us directly to the incredible instruments that first charted them. That uniform cosmic whisper was a profound puzzle. If the early universe was so incredibly smooth, how did it ever give rise to the magnificent tapestry of galaxies and voids we see today? A perfectly even beginning should have led to a perfectly dull and empty cosmos. The answer was hidden in the fine print of that ancient light, in variations too subtle for any instrument to detect. For decades, this was cosmology's great frustration. Then, in 1992, a satellite called the Cosmic Background Explorer, or COBE, changed everything. Its mission was to listen to the universe's background static with a sensitivity never before achieved. What it found were the faintest imaginable wrinkles in the fabric of space. The temperature of the cosmic background is not perfectly identical everywhere. It varies by tiny ripples, mere millionths of a degree, a level of imperfection of just 1 part in 100,000. Think of the surface of a perfectly still pond. From a distance, it looks flawlessly smooth, but up close you see the subtle textures, the tiny dimples and rises created by the air itself. COBE was the first instrument to get close enough to the cosmic pond to see its fundamental texture. These minute fluctuations, these anisotropies, are the universe's genetic code. They are the seeds of destiny. Where the early universe was ever so slightly denser, gravity had a slightly stronger grip, slowly pulling more and more matter in over billions of years. Those over-dense spots became the galaxies and clusters we see today. The less dense regions became the vast cosmic voids. The project scientist John Mather described seeing this data for the first time as seeing the fingerprints of creation. The COBE team presented their findings to the world in a map that looked like a mottled celestial eggshell, a confirmation of the universe's structured beginnings. This was not just a discovery, it was a revelation, earning the team the Nobel Prize and launching a new era of precision cosmology. We finally had the universe's blueprint. Now we needed to learn how to read it. COBE gave us the universe's blueprint, but it was like reading a crucial document through a thick fog. We could see the words were there, the structure was real, but the fine print was a blur. The Planck Space Observatory was the instrument that wiped the lens clean. Launched by the European Space Agency, this marvel of engineering did not just improve the map. It transformed a pixelated sketch into a high-definition masterpiece, revealing the cosmic microwave background with a clarity that was almost unimaginable. Planck measured the temperature of that ancient light across the entire sky, detecting variations of a few millionths of a degree. It even measured its polarization, a subtle property that tells us about the very dynamics of the universe's birth. This was not just a sharper picture, it was a deeper reading of the universe's genetic code. With this data, scientists could determine the cosmos's vital statistics with phenomenal precision. The universe is 13.8 billion years old. Its contents are a shocking revelation. Only about 5% is the ordinary matter that makes up stars, planets, and us. 27% is the invisible gravitational glue of dark matter, and a dominant 68% is the mysterious force of repulsive gravity known as dark energy, the engine driving the cosmic acceleration. The Planck map is a Rosetta Stone for cosmologists. Its intricate pattern of hot and cold spots is not random. It is a frozen record of the physical conditions in the primordial universe, encoding the density of matter and the precise recipe of its ingredients. As Planck scientist Jan Tauber noted, the mission gave us a treasure trove of data, and the universe we see is just the tip of the iceberg. This high-fidelity map is now the primary dataset we use to test our most fundamental theories of physics, from the nature of gravity to the behavior of particles at energies no earthly collider can ever reach. But what do these specific patterns of hot and cold actually mean for the cosmos? They are the echoes of sound waves that traveled through the newborn universe, a story written in the language of cosmic music. Those delicate ripples in the cosmic background are a frozen symphony. The hot and cold spots we see are not random static. They are the fossilized imprint of sound waves, colossal pressure waves that raced through the seething plasma of the infant universe. Think of the early cosmos as a vast, dense fluid ringing like a bell. Where the fluid was compressed, it was slightly hotter and denser. Where it was rarefied, it was slightly cooler. When the universe became transparent, this pattern of peaks and troughs was instantly frozen into the light, creating the temperature map we observe today. But why do denser regions show up as colder spots in the microwave background? This is due to a subtle cosmic tug of war known as the Sachs-Wolfe Effect. A region with extra mass has a stronger gravitational pull. A photon of light trying to escape from that deeper gravitational well has to expend energy, and as it climbs out, it loses a tiny bit of that energy. Since a photon's energy defines its temperature, this loss makes it appear ever so slightly colder to an observer today. Conversely, a photon escaping from a less dense region, a shallower well, has an easier journey and appears slightly hotter. The most striking feature of this pattern is a specific, dominant size for these spots. They appear about 1 degree across in our sky, a size that acts as a cosmic standard ruler. This measurement is profound. It tells us exactly how far a sound wave could travel from the Big Bang until the universe became transparent, a journey of 380,000 years. This distance is a rigid measuring stick. By seeing how big this ruler appears in our sky, we can deduce the geometry of the universe itself. The fact that we see it at precisely 1 degree confirms a critical prediction that we live in a flat universe. This flatness is a direct consequence of the universe's explosive initial growth spurt, the period of cosmic inflation. Beyond the geometry, the statistics of these ripples are a direct window into the universe's quantum origins. The specific distribution of the spots, their varying amplitudes and spacing, match the pattern of quantum fluctuations that were born in the first fraction of a second of time. Inflation then stretched these microscopic quantum jitters to astronomical proportions, imprinting them onto the fabric of space. These magnified quantum seeds are the ultimate origin of every structure we see. That faint cold spot over there, over billions of years, collapsed under its own gravity to become a supercluster of galaxies. That subtle hotspot became a vast cosmic void. But for these seeds to grow into the cosmic web we see today, they needed a scaffolding, an invisible skeleton to guide their growth. This is where the true mystery deepens with the introduction of a ghostly, dominant substance, dark matter. The cosmic symphony was orchestrated by an invisible hand. Ordinary matter, the stuff of stars and planets, was not the primary actor in this ancient drama. It was merely a tracer, a visible die following the currents of a far more dominant but unseen force. This is the ghost in the cosmic machine, dark matter. Its nature remains one of physics' greatest mysteries, yet its signature is etched with stunning clarity into the ripples of the cosmic microwave background. Dark matter does not interact with light at all. It is completely transparent, invisible to our most powerful telescopes, but it possesses mass and therefore it exerts a powerful gravitational pull. In the primordial universe, while ordinary matter was a searing, opaque plasma, dark matter was already at work. It began to collapse under its own gravity, forming vast, invisible scaffolds, gravitational wells that would shape everything to come. Ordinary matter, the protons and electrons, was trapped in a constant battle. Gravity from the dark matter wells tried to pull it in, but it was constantly being pushed outward by the immense pressure of radiation. For hundreds of thousands of years, this cosmic tug-of-war raged, with ordinary matter sloshing in and out of those invisible pits. When the universe finally cooled and became transparent, that motion was frozen in place. The photons of the CMB carry the final snapshot of that struggle. The specific pattern of hot and cold spots we observe is a direct recording of this dynamic. The relative heights of the peaks in the CMB's power spectrum, the precise volume of its cosmic notes, acts as a cosmic scale. It weighs the amount of ordinary matter against the amount of dark matter. The data is unequivocal. For the pattern we see to make sense, dark matter must outweigh normal matter by a factor of about 5 to 1. Without this invisible scaffolding, the acoustic peaks would have a completely different shape. The gravitational wells would have been far too shallow to collect the ordinary matter efficiently. The magnificent cosmic web of galaxies and clusters would never have formed. The universe would be a much darker, emptier, and simpler place. the CMB provides the most robust evidence we have that most of the matter in the universe is something we cannot see, a shadowy architecture that defines the visible world. Yet, even this dominant, invisible matter is not the final word on the cosmos's destiny. A different, even more perplexing force was waiting in the wings, one that would not build structure but ultimately tear it apart. But the universe's blueprint holds clues to an even deeper mystery, one that shapes its ultimate fate. The largest patterns in the cosmic microwave background are not just a relic of the past. They are a living record, subtly altered by everything the light has passed through on its 13.8 billion-year journey to us. One of the most profound alterations is known as the integrated Sachs-Wolfe Effect. Imagine a photon of this ancient light traveling through space. It passes by a massive cluster of galaxies, a deep gravitational well. As the photon falls into this well, it gains a small amount of energy, making it appear slightly hotter. But as it climbs out the other side, it loses that energy again, returning to its original state. This would be a perfect, energy-neutral round trip in a universe where the expansion was constant. However, we do not live in that universe. Dark energy is causing the expansion to accelerate. This acceleration gradually weakens the gravitational wells over cosmic time. So when our photon climbs out of the well, it finds the walls are a little less steep than when it fell in. It does not have to expend all the energy it gained. It emerges with a tiny net gain, appearing as a very subtle, very large-scale hotspot in the CMB. This is the fingerprint of dark energy, a whisper of evidence written directly into the oldest light we can see. The signal is incredibly faint, but by meticulously comparing the CMB map with charts of millions of distant galaxies, scientists have detected this telltale correlation. It stands as independent, powerful evidence that something is indeed pushing the cosmos apart. This discovery, alongside the stunning observations of distant supernova, confirmed a shocking new reality. The universe is not just expanding, its expansion is accelerating, driven by a repulsive force that overwhelms gravity on the largest scales. This revelation was so monumental, it earned the Nobel Prize in Physics in 2011. The cosmic microwave background has given us our most complete inventory of the cosmos, revealing a universe where the familiar world of atoms is a mere 5%, overshadowed by dark matter and dominated by the enigmatic push of dark energy. Yet for all it tells us about the universe at 380,000 years old, the CMB's true story begins much, much earlier. Its patterns are a direct echo from the first fleeting moments of time, from a period of unimaginable transformation that set the entire cosmic story in motion. The primordial ripples we see in the cosmic background have a profoundly strange origin story. They were not born on cosmic scales but on quantum ones. To explain both the stunning large-scale uniformity of the universe and the existence of these specific wrinkles, physicists were driven to a radical idea: cosmic inflation. This theory proposes that in the very first fraction of a second, the universe underwent a growth spurt of almost unimaginable speed, expanding exponentially faster than the speed of light. In that fleeting instant, a subatomic volume of space was blown up to a size larger than our entire observable universe. This explains the smoothness. Regions that were once in contact were stretched far apart, creating the uniform canvas we see. But inflation did something even more remarkable. The quantum world is never perfectly still. It is a seething foam of virtual particles popping in and out of existence. During inflation, these microscopic quantum jitters, these tiny fluctuations in the energy of space itself, were stretched along with everything else. What were once quantum fuzz on a subatomic scale were magnified to become the grand density variations that seeded the cosmos. The theorist Alan Guth famously called this the ultimate free lunch, a universe born from a tiny, energetic fluctuation. The pattern of hot and cold spots in the CMB is our strongest evidence for this incredible event. The statistics of the ripples, their distribution and size, match the predictions of inflation with breathtaking precision. They are nearly scale invariant, meaning the fluctuations look similar on all size scales, and they follow a Gaussian or random bell curve distribution, just as quantum mechanics would suggest. Cosmologists are now hunting for more subtle signatures in this pattern, clues that could tell us which specific model of inflation is correct. They look for a slight tilt in the spectrum of ripples, indicating how the strength of fluctuations changes with scale. They search for an even more elusive signal, the fingerprint of primordial gravitational waves. These would be ripples in the very fabric of spacetime itself, generated by the violent tremors of the inflationary expansion. Detecting them would be like hearing the echo of the Big Bang's shout. This quantum genesis for the entire cosmos means that the largest structures we see, from galaxy clusters to vast cosmic voids, are ultimately the magnified ghosts of quantum fluctuations. The universe began not with a bang, but with a whisper, a quantum whisper that was stretched into the blueprint for reality. The ultimate prize in this cosmic treasure hunt is not a temperature, but a twist. We are searching for a subtle curl in the very polarization of the cosmic microwave background, a pattern known as B modes. Think of the CMB light as having a specific orientation, like the grain in a piece of wood. Most of the patterns we observe are simpler, stretching and compressing in straight lines, known as E modes, but B modes are different. They represent a curling, a swirly pattern in the fabric of the ancient light itself. This signature is the unique fingerprint of primordial gravitational waves. These are not waves in water or sound waves in air. They are ripples in the fabric of spacetime itself, vibrations sent coursing through the cosmos during the violent inflationary expansion. Detecting them would be like feeling the tremors from the Big Bang's first shudder. It would be a direct probe of physics at energy scales 1 trillion times higher than anything we can create in the Large Hadron Collider, offering a breathtaking window into the moment when the fundamental forces of nature were likely unified into a single, supreme force. The hunt for this signal is a story of immense hope and meticulous caution. In 2014, a team using a telescope at the South Pole called BICEP-2 announced a possible detection. The scientific world held its breath. Could this be it? The answer, after painstaking analysis with data from the Planck satellite, was a sobering no. The swirling pattern they saw was largely the result of interstellar dust within our own galaxy, a cosmic mirage. Yet the quest is far from over. It continues with even more sensitive experiments in the world's most extreme environments, from the frigid, dry air at the South Pole to the thin, clear atmosphere of the Chilean high desert. These telescopes are technological marvels, pushing the very limits of detection to listen for this faintest of cosmic whispers. Why is this search so important? The amplitude or strength of these B-mode signals would directly tell us the energy scale of inflation. Was it a gentle swell or a cataclysmic explosion? This single measurement would act as a cosmic filter, instantly ruling out countless theoretical models and pointing toward the one true history of our universe's birth. As cosmologist Ko Lin Kuo, a key designer of the BICEP telescopes, stated, "It is the smoking gun for inflation." This relentless search represents the absolute frontier of cosmic microwave background research, a direct attempt to touch the very first moments of time. While we peer back toward that ultimate beginning, The CMB also holds a detailed record of everything that happened next, a chronicle of the universe's growth and evolution over billions of years. That frozen symphony of the early universe left behind a permanent cosmic echo. The hot and cold spots we see are more than just a temperature map. They are the fossilized crests and troughs of sound waves that once raced through the primordial plasma. These were not gentle whispers but colossal pressure waves, tsunamis of compressed matter and energy traveling at over half the speed of light. For nearly 400,000 years, this cosmic bell was ringing, with waves propagating outward from every slight overdensity. Then, in an instant, the music stopped. When the universe became transparent and the plasma cleared, those waves were frozen in their tracks, their final positions imprinted forever on the sky. This moment created a fundamental yardstick woven into the fabric of the cosmos, a standard ruler known as the Baryon acoustic oscillation scale. It is the exact distance one of those sound waves could travel from the Big Bang until the universe became transparent. That distance is about 500 million light-years. This is not just a theoretical number, it is a physical size we can observe. The most striking feature in the CMB, that 1 degree wide hot and cold spot pattern, is the direct imprint of this ruler on the sky. But the story does not end there. This same standard ruler is also visibly stamped onto the universe we see around us today. When we create three-dimensional maps of millions of galaxies, we do not see a random distribution. We find that galaxies are slightly more likely to be separated by this specific 500 million light-year distance than any other. It is as if each of those primordial overdensities was surrounded by a spherical shell, a ripple in space where matter preferentially collected as the wave expanded and then froze. We are essentially seeing the fossilized bubbles of those ancient sound waves, a ghostly imprint on the cosmic web. This gives astronomers a powerful and direct way to measure the expansion of the universe. By comparing the apparent size of this Baryon acoustic oscillation ruler in the ancient CMB to its size in the local, modern universe, we can measure how much space has stretched over billions of years. It acts like a calibrated tape measure embedded in the cosmos itself. These measurements provide stunning, independent confirmation of dark energy. The local universe shows that this standard ruler is larger than we would expect if the cosmos were coasting, proving that the expansion has been accelerating, stretching that cosmic tape measure faster and faster. This intricate connection between light and matter, between the infant cosmos and the present day, is further revealed through another subtle and beautiful effect imprinted on the cosmic background radiation. The journey of that ancient light is a 13.8 billion-year story of cosmic encounters. As the photons from the cosmic microwave background raced across the universe, their paths were not perfectly straight lines. They were subtly warped and deflected by the gravitational pull of every galaxy cluster and dark matter halo they passed. This phenomenon is gravitational lensing, and it leaves a unique fingerprint on the CMB. The effect is incredibly subtle, not the dramatic arcs we see in images of distant galaxies, but a gentle shearing, a slight smearing of the original hot and cold spot pattern. Think of looking at a printed page through the bottom of a glass. The words are still there, but their shapes are slightly distorted. By meticulously measuring these tiny distortions across the entire sky, scientists can perform a remarkable feat of cosmic cartography. They can trace the gravitational influence of all the matter, both seen and unseen, that lies between us and the edge of the observable universe. The Planck satellite did exactly this, using the CMB as a backlight to illuminate the cosmic web in its entirety. The resulting map is breathtaking. It shows the vast filamentary structure of dark matter, a ghostly skeleton upon which the visible galaxies are merely decorative lights. This lensing map is powerful because it is a direct census of mass, completely independent of starlight. It allows us to watch the universe grow up by measuring how much the lensing signal has strengthened over cosmic time. We can test whether structures are assembling at the rate predicted by our theories of gravity and dark matter. Any discrepancy could point to entirely new physics, suggesting that gravity itself behaves differently on the largest scales. This means the cosmic microwave background is far more than a pristine baby picture. It is a living document, a palimpsest that has been written over by the entire history of the cosmos. Its original message subtly edited by every structure it has encountered on its epic voyage to our telescopes. Another profound edit was made when the first stars and galaxies ignited. That ancient light carries the shadow of the universe's first dawn. For hundreds of millions of years after the Big Bang, the cosmos was a dark, simple place filled with neutral hydrogen gas. Then something extraordinary happened. The first stars and galaxies ignited, and their brilliant, furious light began to flood the void. This was not the gentle starlight we know today. These were colossal, short-lived behemoths, pouring out intense ultraviolet radiation. This radiation was so powerful it had enough energy to rip electrons away from the neutral hydrogen atoms that filled all of space, reionizing the universe in a process we call cosmic reionization. This event marked the end of the cosmic dark ages and the birth of the first luminous structures, a transformative epoch that fundamentally changed the nature of the cosmos. And its signature was left directly on the cosmic microwave background. As those primordial CMB photons continued their epic journey, they encountered this new sea of free electrons. Most passed through unscathed, but a small fraction of them scattered off these electrons. This scattering did two things. It subtly erased some of the very small-scale temperature fluctuations in the CMB, smoothing out the finest details of its pattern. More importantly, it imprinted a specific, large-scale polarization on the light, creating what we call E-modes. Think of this like sunlight glinting off the surface of a lake. The light itself becomes organized, its waves aligned in a particular direction by the interaction. By meticulously measuring these large angle polarization patterns, scientists can work backwards to determine the optical depth of the universe. This single number tells a profound story, revealing when and how quickly reionization occurred. Data from the Planck satellite suggests this process was not a sudden, dramatic flash, but a relatively drawn-out event, beginning around 400 million years after the Big Bang and peaking about 550 million years after it. This polarization is far more than just a record of reionization, however. It is a rich, untapped source of information, a secondary channel of communication from the early universe that carries its own unique messages about the forces that shaped our cosmic beginnings. The temperature map of the cosmic microwave background is only half the story. To read the universe's full history, we must also pay attention to the direction in which its ancient light is vibrating. This property is called polarization, and it adds a rich, hidden layer of narrative to the cosmic afterglow. Think of the CMB light not just as a color or a temperature, but as a wave with a specific orientation, like the grain in wood or the direction of ripples on a pond. This polarization was imprinted at two key moments. The first and most significant occurred during the universe's very last scattering, when photons bounced off electrons for the final time before being set free. This scattering process organized the light, stamping it with a specific, curl-free pattern known as E-mode polarization. You can picture this as a series of radial patterns and straight lines, a kind of cosmic fingerprint left by the density variations in the primordial plasma. Because this signal was created at the very beginning and is relatively clean, it offers a less contaminated view of the infant universe than the temperature data alone. Later astrophysical events, like the light from galaxies, have a much harder time mimicking this specific polarization signature. This purity allows scientists to measure the universe's fundamental parameters with even greater precision. E-modes help break degeneracies, a term cosmologists use when two different theories can explain the same temperature data. By adding the polarization dimension, we can choose the correct model, sharpening our picture of the cosmos composition and geometry. But there is another, far more elusive type of polarization that theorists dream of finding, a pattern with a distinct swirly, curling character known as B-modes. This signal would be the unique fingerprint of primordial gravitational waves, ripples in space-time generated during the violent exponential expansion of inflation. While E-modes are like the straight, radiating lines of a spiderweb, B-modes would be the circular ripples from a stone dropped in its center. The hunt for these B-modes is the grand prize in modern cosmology. As physicist Brian Keating aptly describes it, polarization is the CMB's final frontier. Unlocking its deepest secrets, however, requires an immense act of cosmic cleaning. Our view of this pristine primordial light is obscured by a fog of foreground emissions, from the swirling dust of our own galaxy to the radio whispers of distant quasars. Next-generation telescopes are now being built, not just to see more deeply, but to see more clearly, filtering out this cosmic static in the relentless pursuit of the universe's very first tremor. That pristine whisper from the dawn of time is buried under a cacophony of cosmic noise. To hear the universe's first message, we must first clear the static from our own cosmic neighborhood. Our view of the cosmic microwave background is superimposed on a brilliant foreground of emission from the Milky Way galaxy itself. Electrons spiraling at nearly the speed of light through our galaxy's magnetic fields generate a diffuse radio glow called synchrotron radiation. Vast clouds of interstellar dust warmed by starlight radiate a steady thermal hum. Even individual spinning dust grains emit their own faint microwave signals. This creates a bright, messy veil across the entire sky, obscuring the subtle CMB patterns beneath. Isolating the primordial signal from this local interference is one of the greatest technical challenges in modern cosmology. It is the ultimate exercise in cosmic cleaning. The key to this monumental data analysis task lies in a fundamental difference between the signals. The cosmic microwave background has the unique spectral signature of a perfect blackbody. Its intensity across different frequencies follows a very specific, smooth curve that was set in stone when the universe became transparent. The foreground emissions from our galaxy do not. Synchrotron radiation, dust emission, and other sources all have their own distinct and uneven spectral fingerprints. To separate them, experiments like the Planck satellite did not just look at the sky in one microwave color. It observed the entire sky in 9 different frequency bands, from very low-frequency radio waves to high-frequency infrared. This multi-frequency approach is like using a sophisticated set of audio filters. Imagine you are in a stadium trying to listen to one quiet conversation. Your brain instinctively focuses on that specific voice, filtering out the roar of the crowd, the announcements on the loudspeaker, and the vendor shouting nearby. By knowing the unique sound of each source of noise, you can mentally subtract them to hear the whisper you need. Planck's 9 frequencies allowed scientists to do precisely this on a cosmic scale. They could create a detailed model of the galactic foregrounds and then, frequency by frequency, pixel by pixel, subtract that bright foreground away. What remains is the cleanest possible map of the cosmic microwave background itself. This painstaking process of foreground removal is a testament to the incredible sophistication of modern data analysis. It is a silent, behind-the-scenes revolution that makes precision cosmology possible. With this clean map finally in hand, we can perform the ultimate reality check, comparing our exquisite observations against the grand theoretical predictions for the birth of the cosmos. This cosmic blueprint, once decoded, becomes the ultimate arbiter of truth for our theories of the universe. The standard model of cosmology, known as lambda cold dark matter, rests upon a surprisingly simple foundation. Its entire framework is defined by just 6 key numbers. These parameters include the density of ordinary matter, the amount of dark matter, the Hubble constant which measures the current expansion rate, and the amplitude of those initial quantum seeds. The intricate pattern of hot and cold spots in the cosmic microwave background is exquisitely sensitive to each one of these numbers. It acts as a cosmic tuning board, where adjusting a single parameter changes the entire symphony. To see how this works, scientists use a powerful tool called the power spectrum, often visualized as a wiggling line on a graph. This chart plots the strength of the temperature fluctuations against their size on the sky. The peaks and troughs of this line are the acoustic peaks, the fossilized notes of the primordial sound waves. The precise position and height of these peaks are not random. They are a direct reflection of the universe's physical conditions. The location of the first peak, for instance, tells us the universe is geometrically flat. The ratio of the second peak's height to the first reveals the density of ordinary matter. The third peak gives us a measurement for the amount of dark matter. By meticulously comparing these theoretical wiggles to the real data from the Planck satellite, cosmologists can tune the 6 parameters until the model's prediction perfectly overlays the observed universe. The result is a fit of breathtaking precision. We can now state the density of dark energy to within 1% and the age of the universe to within a few dozen million years. This remarkable agreement is one of the great triumphs of modern science. The lambda CDM model, refined by the CMB, provides a single, coherent framework that explains everything from the abundance of light elements to the large-scale distribution of galaxies. Yet, this profound success is not the end of the story. A few stubborn cracks have begun to appear in this elegant edifice. A significant tension has emerged around the Hubble constant. The value measured from the CMB, which looks back to the early universe, disagrees with the value measured from supernova and other local probes that look at the cosmos today. The early universe suggests a slower expansion rate, while the modern universe measures a faster one. This is not a small experimental error. The discrepancy is persistent and statistically significant, hinting that our otherwise powerful model may be incomplete. Perhaps dark energy is not a constant but is evolving, or maybe there is a new, unknown type of neutrino. The cosmic blueprint has given us a nearly perfect picture of our universe, but its most tantalizing gift may be the subtle clues pointing toward the physics we have yet to discover. Our most precise map of the cosmos reveals a crack in the foundation. The universe's current rate of expansion, the Hubble constant, is telling 2 different stories depending on how we measure it. When we use the cosmic microwave background as our guide, looking back to the infant universe, we calculate a value of about 67 kilometers per second per megaparsec. This means that for every megaparsec of distance, about 3.3 million light-years, the universe is expanding at 67 kilometers per second faster. But when we use local cosmic landmarks like the pulsing rhythm of Cepheid variable stars and the brilliant flash of Type 1a supernova, we get a different answer entirely. These local measurements consistently point to a faster expansion, around 73. This is not a small rounding error. The gap between these values is significant and stubborn, persisting even as our methods become more and more refined. It is as if the universe's childhood portrait predicts one future, while its current reality shows another. If this tension is real and not some hidden flaw in our measurements, it means our standard model of cosmology is missing a crucial piece. Perhaps dark energy is not constant but is growing stronger over time. Or maybe there is an additional, unexpected type of neutrino or another exotic particle that was influencing the early universe in a way we have not accounted for. This discrepancy is a direct challenge, a cosmic puzzle that could unlock the next chapter in fundamental physics. Beyond this major tension, the CMB map holds other, more subtle oddities. The sky is not perfectly symmetrical. There is a curious and unexpected asymmetry between the northern and southern galactic hemispheres, with one side appearing slightly warmer on average than the other. Then there is the famous cold spot, an area of space that is significantly colder and far larger than our theories can easily explain. It could be a statistical fluke, a simple coincidence in the cosmic data, or it could be something far more profound, like the imprint of a collision with another universe in the vast multiverse. While less statistically certain than the Hubble tension, these anomalies are persistent thorns in the side of a perfectly smooth theory. They remind us that for all we have learned, the cosmos still holds deep mysteries. Resolving these tensions is the driving force behind a new generation of cosmic observatories. From the Simons Observatory in the high Chilean desert to the ambitious space-based concept for LightBird, scientists are building instruments with unprecedented sensitivity. They are not just looking for a clearer picture, they are hunting for the clues that will force our most successful model of the universe to evolve, pushing our understanding of reality itself toward a new frontier. The search for the universe's first tremor demands a new generation of eyes. Across the high deserts of Chile and from the pristine quiet of space, a technological revolution is underway, building instruments of almost unimaginable sensitivity. These are not simply bigger telescopes, they are armies of them. The Simons Observatory and its successor, the ambitious CMB S4 project, plan to deploy hundreds of thousands of tiny, supercool detectors across their massive arrays. Their singular focus is the hunt for the primordial B mode, that elusive curl in the CMB's polarization that would be the definitive echo of inflation. Each new detector acts like another ear listening for a whisper in a storm. With this collective power, these observatories will either finally capture that faint signal or push the upper limits on its strength so low that they will rule out entire families of inflationary theories, forcing a fundamental rewrite of our cosmic origin story. But the quest does not end on the ground. Proposed space missions like LightBird are designed to soar above the obscuring blanket of Earth's atmosphere, settling into a stable gravitational pocket a million miles away. From this silent vantage point, free from atmospheric noise and seasonal interference, it will conduct the most pristine, all-sky survey of the CMB's polarization ever attempted. Its mission is to scan the entire cosmic microwave background with a painstaking patience impossible on Earth, searching for the large-scale B-mode pattern that ground-based telescopes might miss. The scientific harvest from these future observatories will be staggering, extending far beyond the hunt for gravitational waves. Their ultra-deep maps of the CMB's temperature and E-mode polarization will act as cosmic microscopes. They will measure the total mass of neutrinos, those ghostly particles that flood the universe, potentially revealing if they make up a portion of the mysterious dark matter. They will dissect the epoch of reionization with forensic detail, revealing the precise timeline of when the first stars and galaxies ignited and began to sculpt the cosmos. The sheer volume of data will be so immense that it will likely uncover anomalies and phenomena we cannot even predict today, opening new chapters in physics. Achieving this vision requires a breathtaking leap in engineering. It pushes the very frontiers of cryogenics, developing systems that can cool thousands of detectors to within a fraction of a degree above absolute zero. It demands revolutionary advances in detector design to make them vastly more sensitive and in data analysis techniques to process an ocean of raw information. These experiments are monuments to human curiosity, a global effort to build the most perfect time machine possible, one that peers not just into the past, but into the very laws of physics at the moment of their creation. This ancient light is so sensitive it can weigh the universe's most elusive particles. The cosmic microwave background holds a census of the primordial neutrino sea, a relic population of ghostly particles that have been streaming through space since the first second of the Big Bang. Neutrinos are so light and weakly interacting that trillions of them pass through your body every second without a trace. They are nearly impossible to catch in a laboratory, yet they left a distinct imprint on the infant cosmos, an imprint we can still read in the CMB. Their influence is twofold. First, in the early universe, these neutrinos were a dominant form of energy, racing outward at nearly the speed of light. This sea of relativistic particles contributed to the overall energy density, which in turn affected how fast the universe was expanding before the CMB was released. This altered expansion rate left a subtle but measurable mark on the relative heights of the acoustic peaks in the CMB power spectrum. The second effect is even more telling. Unlike dark matter, which clumps together to form gravitational wells, neutrinos are aloof. They free stream, meaning they travel in nearly straight lines, refusing to cluster on small scales. This behavior acts as a drag on the formation of the very smallest structures. Imagine trying to build a sandcastle while a fine, constant wind blows through the grains. The large structures can still form, but the finest details are smoothed away. That is what neutrinos did to the cosmos, suppressing the growth of the tiniest wrinkles in the cosmic web. By combining the exquisitely detailed CMB map from Planck with three-dimensional surveys of millions of modern galaxies, cosmologists have performed a remarkable feat. They have placed a firm upper limit on the sum of the masses of all three known neutrino types. The current constraint is staggering. Neutrinos must be incredibly light, with a combined mass of less than 0.1 electron volts. To put that in perspective, they are at least 1,000,000 times lighter than an electron, the next lightest particle we know. The next generation of CMB observatories is not aiming to just constrain this mass, but to measure it directly. Detecting this tiny number would be a monumental discovery in fundamental physics, but it will not happen in a deep underground lab. It will be achieved by staring into the ancient sky, using the entire universe as our particle detector. The cosmic microwave background has transformed cosmology into a laboratory for testing the most profound laws of nature. The idea of a multiverse emerges naturally from the most powerful versions of cosmic inflation. If our universe underwent that exponential stretching, then the process may not have stopped everywhere at once. According to the theory of eternal inflation, the rapid expansion could be a runaway chain reaction, ceasing in localized pockets to create isolated bubble universes while continuing unabated everywhere else. In this breathtaking scenario, our entire cosmos is just one bubble in an infinite, frothing sea of universes, each with its own unique properties. The fundamental constants we consider immutable, like the strength of gravity or the mass of an electron, could be random variables in this vast cosmic lottery. Some bubbles might have physics that instantly collapses them, while others could be sterile, empty voids. We find ourselves in a bubble where the numbers just happen to allow for galaxies, stars, planets, and life. This is the anthropic principle in its most dramatic form. a potential explanation for why our universe seems so finely tuned. The precise, small value of dark energy we measure from the CMB, a number that seems oddly conducive to the long-term growth of structure, might not be a fundamental law but a local environmental accident. While we cannot journey to another bubble universe to test this idea, the cosmic microwave background might hold indirect, coded messages about this greater reality. The key lies in the detailed statistics of the primordial ripples. The standard model predicts these fluctuations should follow a Gaussian, or purely random, bell curve distribution. But certain complex models of inflation that also predict a multiverse could have imprinted subtle deviations from this randomness, patterns known as non-Gaussianity. Finding such a signature would not prove the multiverse exists, but it would point toward the kind of physics that makes such a vast reality possible. This places the CMB at the center of a profound philosophical shift. It forces us to consider that our universe may not be a unique creation, but one of countless cosmic experiments, its blueprint hinting at a reality far grander and more strange than we ever imagined. That faint pattern on the cosmic microwave background is a message from the quantum world. These ripples are the ultimate cosmic inheritance, a direct link between the behavior of the universe on its very smallest scales and its grandest structures. The microscopic, probabilistic jitter of quantum fields in the newborn universe, a seething foam of virtual particles, was the raw material for everything. During the violent exponential expansion of inflation, these subatomic fluctuations were stretched to astronomical proportions. What was once a tiny quantum hiccup in a volume smaller than an atom became a vast region of slightly higher density, spanning millions of light years. This process transformed random, ghostly flickers into the concrete seeds for galaxies. The cosmic background radiation provides the most direct evidence we have for this incredible transformation. It shows us that the rules governing the spin of an electron and the collision of photons also sculpted the great cosmic web. This establishes a profound bridge between quantum field theory, which describes the chaotic dance of the very small, and general relativity, which governs the smooth geometry of spacetime on large scales. These two pillars of modern physics have been famously difficult to reconcile in a single, unified framework, yet the CMB demonstrates that they were not just compatible in the early universe, they were collaborators. They worked in concert to forge the reality we inhabit. This realization has sparked a revolutionary cross-pollination between cosmology and particle physics. Cosmologists now use the entire universe as their laboratory, with the CMB serving as the data readout from the highest energy experiment ever conducted, the Big Bang itself. The patterns frozen in that ancient light allow us to probe physics at energy scales 1 trillion times beyond the reach of the Large Hadron Collider. We are not just mapping the heavens, we are performing fundamental particle physics by observing the aftermath of creation. This forces a dramatic reconsideration of reality itself. The solid, predictable cosmos around us, with its galaxies and voids, appears to be the magnified echo of a fundamentally probabilistic and uncertain quantum beginning. The universe did not start with a definite shape, but with a spectrum of possibilities, and we are living out one of those potential histories. The universe might be a hologram, and its projection screen could be all around us. This is the radical premise of the holographic principle, an idea born from the strange physics of black holes. When matter falls into a black hole, it seems to vanish, yet the laws of physics demand that information cannot be destroyed. The solution theorists found was as elegant as it was bizarre. The information about everything swallowed by the black hole is not lost in the interior, but is instead perfectly encoded on its two-dimensional boundary, the event horizon. The three-dimensional reality inside is, in a profound sense, a projection of that two-dimensional data. Could this same logic apply to the entire cosmos? Some physicists speculate that our vast three-dimensional universe, with all its galaxies and stars, might itself be a holographic projection from a distant two-dimensional surface. And if that is true, where is this cosmic film? One compelling candidate is the cosmic microwave background. Think of the CMB as the ultimate celestial sphere, a giant bubble surrounding us, etched with a pattern of hot and cold spots. This bubble is a two-dimensional surface containing an immense amount of information. Could that information be the source code for the three-dimensional reality we experience within it? The idea is that every particle, every force, every event in our world is a decoded representation of data stored on that primordial screen. This would mean the universe is not what it appears to be, that its fundamental nature is informational. The strange, non-local correlations we see in the CMB sky, where points seemingly too far apart to ever communicate are mysteriously linked, might make perfect sense in this framework. In a hologram, every part of the image contains information about the whole. The entire structure is deeply interconnected, just as the quantum fuzz that seeded the cosmos was. While this remains a highly speculative frontier of theoretical physics, it demonstrates the CMB's power to push us toward the absolute limits of reality. It forces us to ask not just what the universe is made of, but what it truly is. The ancient light is more than a relic. It is a constant invitation to question the very nature of space, time, and information itself. Our cosmic map, for all its precision, has a fundamental and unbreakable resolution limit. This is the challenge of cosmic variance, a statistical truth that reminds us we are prisoners inside a single experiment. We have only one universe to observe, and the cosmic microwave background is a single, unique snapshot of its infancy. When we look at the very largest scales on this map, like the broadest temperature waves, we are essentially measuring a sample size of one. We cannot know if the patterns we see are truly representative of the entire cosmos, or if they are just a statistical fluke of our particular patch of space, our Hubble volume. Think of it like trying to understand the global climate by measuring the weather in one single city for one single day. Your data is real, but is it typical of the entire planet? That lingering cold spot, or the curious asymmetry between hemispheres, might not be a profound anomaly pointing to new physics. They might simply be the cosmic equivalent of flipping a coin and getting heads 10 times in a row. It is a rare but possible outcome within the rules of chance. This means some of the universe's biggest mysteries, the true nature of its largest scale features, may be questions we can never definitively answer. We are embedded within the system we are trying to understand, unable to step outside for a perfectly objective, God's-eye view. This inherent limitation defines the ultimate precision of all cosmology, a final horizon for our knowledge. And yet, this humbling constraint makes our achievements all the more staggering. Within the confines of this one observable universe, we have managed to decode a blueprint of breathtaking detail, reconstructing a history of 13.8 billion years from a single ancient whisper. That mottled celestial map has become far more than a scientific dataset. It has transcended the pages of academic journals to become a modern cultural icon, a symbol of humanity's deepest yearning to understand its place in the cosmos. We call it the universe's baby picture, a phrase that perfectly captures its profound yet accessible meaning. This image represents a shared heritage for every single person on Earth. We are all bathed in this ancient light, a constant, gentle rain of photons that have been traveling for 13.8 billion years to reach us. It is a humbling and unifying thought. We live on a pale blue dot, but we are connected to the entire observable universe through this primordial afterglow. The story of how we captured this image is a monumental epic of human curiosity. It is a tale woven from the data of space satellites like COBE and Planck, from high-altitude balloons drifting over the Antarctic ice, and from massive ground-based telescopes in the world's most remote deserts. This was not the work of a lone genius, but a collective endeavor involving thousands of scientists, engineers, and technicians across generations and continents. Their shared goal was to read the universe's first message, and in doing so, they gave us all a new origin story. This cosmic narrative has now entered our public consciousness. You can see the CMB map projected in dazzling planetarium shows, featured in documentaries that bring the cosmos into our living rooms, and reimagined in art installations that translate its subtle temperature variations into sound and color. These artistic interpretations make an abstract and incredibly complex field tangible. They allow us to feel a connection to the cosmos, to grasp the sheer scale of our history from the quantum vacuum to the complex universe we see today. This shared connection does more than just inspire awe. It ignites curiosity in a young person gazing up at a starry sky, wondering how it all began. It fuels the imagination of the next generation of scientists, engineers, and philosophers who will take these first revelations and push them even further. The cosmic microwave background is our collective inheritance, a reminder that our story is written in the light of the Big Bang itself. The faint whisper of the cosmic microwave background arrives at our telescopes as a chaotic torrent of digital noise. Translating this raw data stream into a pristine map of the infant universe is one of the greatest computational challenges in all of science. Instruments like the Planck satellite did not simply take a photograph. They generated a relentless flood of time-ordered data, a log of how each of its supercooled detectors twitched and responded as they scanned the sky over years. This raw data stream, measured in terabytes, is a maddeningly complex mix of signals. It contains the faint CMB signal, the brilliant emission from our own galaxy, the hum of instrumental noise, and the subtle glitches from cosmic rays. Untangling this cosmic knot requires a Herculean digital effort. The first step is to understand the instrument itself with incredible precision. Scientists must model the exact shape of each detector's beam, how it perceives a single point of light as a tiny blur. They must calibrate its sensitivity and meticulously characterize its unique noise patterns, a constant hiss that must be digitally subtracted. Only then can they begin the real work of reconstruction, turning billions of individual detector readings into a single, coherent picture of the sky. This is where supercomputers become our essential partners in discovery. To separate the cosmic signal from the galactic foreground, researchers run millions of Monte Carlo simulations. These are virtual experiments creating synthetic skies with different combinations of CMB patterns, dust emission, and instrument noise. They run their analysis algorithms on these simulated datasets again and again, testing how well they can recover the original input. This process allows them to understand the statistical uncertainties and potential biases in their final map, ensuring that a supposed cold spot is not just a random fluctuation in the detectors or a patch of galactic dust. The final Planck maps, those iconic images of the mottled universe, are not a direct observation. They are the product of years of painstaking analysis by large international collaborations, a digital tapestry woven from countless lines of code running on some of the most powerful supercomputers on Earth. This endeavor fundamentally redefines cosmology. It is no longer a science driven by telescopes alone, but a big data enterprise reliant on advanced algorithms and raw computing power to listen for the universe's first message. The sophistication of this entire process, from the first bit of data to the final map, is what grants us the phenomenal precision to weigh dark matter, measure the age of the cosmos, and hear the echo of its quantum birth. We can now listen to the cosmic background. Scientists and artists have transformed the universe's baby picture into a symphony, a process known as sonification. By scanning across the map of the cosmic microwave background, they assign a musical pitch to each temperature reading. Hotter spots sing out as higher notes, while colder regions resonate with deeper tones. The result is a ghostly, ethereal melody, a direct audio translation of the primordial ripples that seeded our cosmos. This is the sound of the universe's birth, played back after 13.8 billion years of silence. But this is far more than an artistic endeavor. Our ears can sometimes detect subtle patterns and rhythmic structures that our eyes might miss in a complex visual field. A slight dissonance in the chord, a strange repetition in the sequence, could hint at an anomaly buried in the data, offering scientists an alternative pathway to discovery. More profoundly, sonification democratizes this cosmic message. It allows anyone, regardless of their scientific background, to experience the Big Bang directly. You are not just looking at a graph, you are hearing the foundational vibrations of reality. This multi-sensory engagement reminds us that the universe is not a dry collection of mathematical parameters. It is a dynamic, physical entity that we can see, measure, and now hear. The haunting chords of this cosmic symphony bring our journey full circle, connecting the abstract quantum genesis to a sensory experience, making the immense story of creation feel intimately real. This ancient light is our shared inheritance, a story written across the sky for anyone with the curiosity to read it. Our journey has taken us from the first quantum shudders of spacetime to the magnificent cosmic web of galaxies, all decoded from subtle ripples in a faint, cold glow. The cosmic microwave background has been our Rosetta Stone, a universal translator that allowed us to take the temperature of the infant cosmos and weigh its invisible components. We have confirmed its explosive birth in inflation, mapped the ghostly scaffolding of dark matter, and felt the repulsive push of dark energy. This is not just a collection of facts, it is a coherent origin story for everything. The lingering mysteries, like the tension in the universe's expansion rate, are not failures. They are the signposts for the next generation of explorers, the questions that will drive our telescopes and our minds toward an even deeper understanding. So the next time you find yourself under a clear night sky, remember that you are not just looking out into space. You are looking back in time, bathed in the gentle rain of the universe's first light. You are a living witness to the afterglow of creation itself. We would love to hear what parts of this cosmic story resonated most with you. Share your thoughts and questions in the comments, and subscribe to join us as we continue exploring the greatest mysteries of the